Keepsafe Tech Talks, number 8 or 9. Welcome to Keepsafe. Our mission is to make digital privacy as easy as closing a door. And I'm really happy to have all of you here, and a lot of the Keepsafe team is here also. So if you're interested in what we're doing, please know that we're hiring, so talk to Philip. If you're interested in learning more about privacy and how average people can make use of it in their digital lives. I'm really glad that we can revive this series that we neglected a little bit last year, and have Clement from Layer here, who's going to talk about stream-based data synchronization. I would like to make a nice joke about what he's talking about, but
go ahead.
I better not. So with this, give it up to Clement.
All right. Good evening, everybody. So tonight I'm going to be talking about a very specific way to synchronize a shared data model using stream-based data synchronization. I'll give a case for it, demonstrate how to implement it. We'll even go through data structures and where it actually works well and where this thing falls apart. Let me first introduce myself. So my name is Clement Verdnik, and I got introduced to programming very early in my life, and I've always been interested in low-level programming, things like audio and video processing, anything where you have to process things in like really quick and deliver it in near real time. I had an opportunity to work on a lot of cool projects, got familiar with the iOS SDK since it came out. Then joined my first startup called Vox.io, where we built this cool telephony/messaging app for both web and mobile. Then later started a company with my friends called Layer.com, where we built this awesome messaging platform. It's also where I got an opportunity to work on a lot of prototypes that involved a lot of data synchronization, and really got obsessed with it. So what is data synchronization? It's basically very simple. It's having data consistent across devices, across two or more network devices. And I just want to start with a very basic example on how data synchronization actually looks like. So let's just imagine an app where it's just a toggle switch app, right? And if I've got 5 devices in front of me, if I flip that switch on one device, that change should propagate on all other 4 devices. And how would we design such a system? So let's take a quick look at how would we structure the server. So we need a model, something that represents that light switch value. Serialization, deserialization logic, because we'll need to send those changes across the network. Client's kind of the similar model that represents the value, UI that visualizes it. Again, serialization, deserialization logic, since we're going to receive all these changes from the server and also send them to the server. And the data structure should be very simple. It's just, in this case, it's just a single Boolean value that represents the on and off switch. The logic is also very simple. Once a device sends out this data structure, server's job is to just fan out that change to other online clients. This is basically a very basic demonstration of what data synchronization is. And the thing is, we don't think about these things, but we use apps and services that use data synchronization every day. Things like email, messaging, photo sharing, file sharing, text editors where it allows multiple users to work on the same document at the same time, even multiplayer games. So let's take a quick look at what types of data we even synchronize. So file synchronization, we mentioned file sharing. It's where we try to keep the directory structure along with the files kind of the same on another machine. So if I drop a file into a folder, I want that file also to appear on another computer. Things like Dropbox, iCloud, Google Drive, all these things are basically file synchronization. Text synchronization, we're all familiar with source control. This is basically text synchronization. It requires a lot of manual work, but at the end of the day, it's still synchronization. Or data model synchronization. We just had an example with that light switch earlier. So we know what kind of data we synchronize, but how do we actually do it? So one way is to just transfer the whole thing, everything, basically the whole data set. That's also known as a wholesale transfer. Think of, you have to just fetch a JSON object from the server that kind of represents the weather forecast or an RSVP list. The problem with this kind of approach is that it's kind of hard. I mean, it only works good if you're dealing with small data sets. So if you don't care for the bandwidth as well. But the other problem is also that it's kind of hard to tell what has actually changed since the last time you've fetched that data set from the server. So we need to hold on to the previously fetched data and kind of compare it with the new one. And that costs memory and CPU since you have to kind of iterate through both data sets. So let me just give you a very stupid example. So say you were invited to a private dinner party at a restaurant somewhere, and you come in and you ask the receptionist who's here, who's joined the party, and then the receptionist would just go over the names of people that have joined the party. And now suppose you weren't paying attention and one of the guests left. So you go back to the reception and just ask them what has changed. And then the reception will go over again the list of people that are actually here. So you kind of have to think what has actually changed and compare those two lists of people that he named. So it would be much easier for you and for him if he just tell you the last thing that has actually happened. He would just go over his book and find out the last record. So you could basically take that change, that delta, and apply it to your mental data model. So I mentioned a delta. So what's a delta? This is a very basic way to describe differences between two data sets. And how do we encode them? So we've got, we usually deal with three sorts of operations. So let's say that you want to, you basically want to add an item into a collection, and that's basically one operation type, or you want to update an existing element in a collection, or you want to delete an existing element from a collection. And collections could be sets, arrays, dictionaries, whatever. And it also works on any kind of data structure, even binary blobs like this. So say I want to update 3 bytes in this binary blob at a certain location. I would just use that delta, encode an update type, and apply it onto the model, or append more bytes at the end of the blob, and use a type of insert. What about if I want to mutate a piece of text? So in this case, I forgot, anybody that's familiar with Swift, I forgot to unwrap an optional over there. I could use a delta that looks like it's basically a diff patch. We're all familiar. Anybody that's done any PR reviews knows this type of delta. The problem with this is, I mean, it works. It's a nice way to encode it, but it's kind of redundant and verbose because it keeps the before and after value. We could just use the same data structure as we did earlier and just use type of insert, since we want to just add that question mark at a certain location, and that gets our model up to date. Or, for example, just custom data structures, like our guest list earlier from the example. One guest left, how would we encode that with that kind of a mutation? So a type of delete, and which one was it, and that's it. And we've got our data set up to date. So now we know how to encode data model mutations, and we finally get to talk about stream-based approach to synchronization. But before we dwell into it, let's just name a few motives why even choose this type of sync. So I mentioned earlier that we want to have a shared data model, so all users would basically see would have the same view of the model. So we don't want to duplicate that data on the server, so we kind of want to minimize the data redundancy, meaning that we don't want to make copies for each user. We also care for speed, so our changes should be very short so that we can send them to the server and onto the other clients as fast as possible. So data structure should be small and simple. We don't want to spend too much time writing big chunks of data to the database. So we want to have fast writes because that also means good concurrency characteristics on the server. Sorry. And that we also want to have a very simple database schema because we want to have it distributable across other nodes so that we can scale the system up easier. And lastly, we want our clients to work independently of the server when it loses the connection. So what's this stream I keep mentioning? If you remember our first example, the light switch example, we had the client was basically receiving a constant flow of light switch changes or a stream of events, if you will. That was a very basic data structure where a wholesale transfer would suffice. But what if we were dealing with a much more sophisticated data structure? So let's imagine another app, like a shared to-do list app, where you have a list of items along with the checkboxes where you can mark them as read, and that all these changes, all users will basically have the same point of view. So how would we structure such a model? So let's go over the app model real fast. So we have a collection with our tasks there, and tasks should be very basic. I mean, it actually should represent the task that we saw on the UI, which is basically a completed state title, and let's give it a color label just for fun. And these tasks can be added, edited, and removed from our collection. So we need methods that support these user actions. That kind of concludes the app model. So we need to turn these user actions into events, which should be very simple data structures, simple and flat. If you remember from the chapter before, we had, when we encode deltas, we kind of have to say what kind of an operation type it is, if it's an insert, update, or delete. And then we've got those properties that actually represent the task state. And we want our events, these data structures, to be serializable. So since we're going to send them through the, across the network to the server and vice versa. So that's the sync model. In case we create it, it's got a type of 0 and the rest of the properties along with it. How would an event look like if we just mutate a task, if we mark it as complete? It's a type of an update, and we reference the task by some ID, and that's basically it. So we now know how these events look like, but how do we get them off the devices? So we need a transport layer, and it's a very basic one. We just need something that's capable of receiving our events from the server and something that's capable of publishing them onto the server. And so we know which part deals with to-do tasks, how to describe our app model changes, and how to send and receive them, these changes basically across the network. And so our app is running now, and it's connected to the server, and it's receiving a live stream of events. An app model will be consistent as long as it's connected to the server, as it's receiving all these events. But in case client drops, offline, or just is missing events because it came online a little bit later, that client would basically end up with an inconsistent model with the server. So that's also a state we know as out of sync. An example would be, what good would an event that describes a task mutation, that it says that there's a task that's been completed, if you haven't even received the event that actually created that task in the first place. So fortunately, that state is recoverable. One way is to just replay all the events that the client has missed while it's been offline. But that means that the server's responsibility not only is to fan out all these live events that are generated, but also to preserve them and provide them for later consumption for the clients that might need them. which brings us to the persistent streams. So think of persistent streams as magnetic tapes or as a storage with a write once, read many behavior, where you're only allowed to append data and you can't mutate anything that's already been written. Or think of it as a journal of all the events that have happened. So how do we know if the client actually has received all the events? We could, do the wholesale transfer, which we discussed about it earlier, but that doesn't scale. Or we can write some integrity check that basically, you could just hash some ranges of your events and match it against server. But that would only indicate that there's some mismatches. But it's actually easier than that. It's really not that difficult to figure out which events the client might have missed. We just need to sequence these events. We have to give them numbers as they get written to the stream. And we also need to update our data model with that sequence number. So what's great about this kind of a sequence is that it's totally reproducible on the client. It's just a linear function. And the only thing that the client needs to know from the server is the latest sequence value or the sequence value of the last event that's been written to a stream. With that, basically, the client could reconstruct the sequence and subtract it with the sequence values of the events that it's got, and then you basically end up with a set of sequences that you're actually missing. This is a very basic implementation in Swift. So now we talked about how these events look like and how they get streamed and discovered, but we never really talked about which part of the logic takes care of generating these events and which logic takes these events and uses them. It's a process we call outbound and inbound reconciliation. So let's talk about outbound reconciliation first. So it's pretty basic. So everything that user touches, all user actions, have to be turned into events. So what's interesting about this is that there's some similarities. These are the user actions, and that's our event model. So it basically describes the same thing. We've got the operation types, and we've got the arguments that we take in through those methods. It's kind of similar to serializing RPC calls or even message passing, if anybody's familiar with that. Anyway, we could have these user action methods just vend these events as they get called. So an example would be I create a task, and that would create a task and also vend out an event that represents it, that change. And then we just need to publish that event on the server, and we're done. Now, inbound reconciliation, it's a process. It's where we get incoming events, and we have to apply them onto our data model. This is a very basic implementation. You have to cover all those three cases: insert, updates, and deletes, which basically mutates our collection or the tasks. But what happens to outbound events when the client's offline? If you remember, if clients are not, if they're missing out on events, it renders their model inconsistent. So it's pretty simple. We just need to kind of buffer those or queue those events for later publication as soon as client actually gets the connection. That can be a persistent queue, so we don't lose them. But we have to be careful that we don't overfill the buffer with redundant events. I'm talking about, let's say that I just tap on the task completion like crazy, and that would generate a lot of the same events over and over. And these events would eventually end up getting written onto the stream as the user actually presses the button. So that kind of extends the edit distance that describes the object mutation. We call this kind of a state as stream pollution. It slows down other clients because they have to discover all these events and then fetch them and then apply them onto the model. It's very easy to basically fix this. We just need to reduce the edit distance basically we need to squash these changes into single events if it's possible. So insert event would merge for insert for a specific object would have to merge with other update events into a single insert event. And an update event would have to merge with the rest of the update events for that specific object into a single update event. And with that in mind, last update event actually defines the final state of those properties that we just mutated. And if there's a delete event in queue, it basically clobbers the rest of the updates or inserts because you don't have to keep everything to reconstruct a deletion. And this is a very simple implementation of how to squash these changes. And having a shared synchronized data model is basically a concurrent system. And in concurrent system, we can experience conflicts with whenever two or more clients, touch the same resource at the same time. An example would be a client deletes a to-do task before another client actually tries to mutate it. And how would we solve such a conflict? One way is to just say, okay, let's bring that deleted task back. And that's also a thing known as last writer wins. Or we just say, no, delete whatever was deleted stays deleted, and that's also known as first writer wins. Or we can just ask the user what to do, just in a form of a alert view. But we kind of want to have our conflict resolution automatic as much as possible. But to have a much better judgment at that, when it comes to automatic conflict resolution, we turn to event ordering. And the way how we model our stream and events is basically considered, our events are considered to be in a total order. It basically means that they are preceded by each other in the same order as they were written to the stream, and that order is basically defined by our event sequence number, because it gets incremented by one. It also means that all clients will apply these changes in the same manner onto their app model. But that requires that clients publish all these outgoing events in a batch, meaning that all these events have to stick together, otherwise there's more chance for a conflict. But with batched writes, it means that we have to have an exclusive lock to our, wherever we write all these events, and that kind of violates our, fast concurrent writes requirement that we mentioned earlier. And there's also another thing with total order. So offline support. So let's say that we've got two online clients, and we, add a task. It appears on another device, and then one device actually drops offline, and we add more tasks to that offline client, and just another one for fun on an online client. And now user hasn't used this app for a week, so these tasks are basically old and stale. And once user actually launches that app and publishes those events onto the stream, these tasks will basically end up at the end of the stream and thus render our app model. It'll look like those tasks were just generated by some user, or in fact are basically old for more than a week in our case. So apparently the total order of events doesn't work well with our offline support. So we turn to causal order. In causal order, there's just one rule. Effects come after causes and never before. In our case, that would be, let's just say that one user saw that there's a buy milk task, and it made him respond to that because he already bought the milk and mark it as read, and that's an effect. So generated event is an effect caused by user taking action or responding to the UI. But the thing is, events should be reconciled in the same order as they were generated by clients. Or in other words, events should be applied onto the model under the same conditions as that model was when those events were generated. And total order apparently cannot guarantee that the events will be written to the stream in the same order as they were generated by other clients. So that means that we cannot rely on the order of the events as they were written to stream. So what's universal across all the devices? So you might be thinking time, right? So let's play with that idea for a little. So let's say we've got two clients. Client A actually starts generating these events first, but it's got a lot of work. It's going to generate a lot of events, whereas client B actually comes into the game a little bit later, but it's got a little less work to do. So his client B's events are going to end up on the stream before client A. So how would we make sure that other clients know which events were generated first? So you might be thinking, all right, let's just encode a timestamp along with our events, and then other clients could basically reconstruct the order how they were generated. Well, the problem with that is that we cannot guarantee that the clock actually runs the same on all devices due to the clock skew. Or even worse, a user might basically mess with his system settings on a mobile device and revert or just change the time. We break our app because those events will be reconciled in an incorrect order, and that makes our app kind of look flimsy. So we turn to version vectors. We want to reconstruct events order as it was perceived by the author based on what happened before information. This basically provides us causality tracking. It's a basic principle in some optimistic replication algorithms. Allows the clients to operate independently from the server. It allows that clock skew or being completely offline. And when all clients eventually do publish their events, when they come back online, it turns other clients into a consistent state, which is also known as eventual consistency. So how do we encode that happened before information? It's pretty simple. We just point to what we saw before this event that we're about to generate. A lot of version vector, synchronization implementations that use version vectors actually make copies, and that doesn't scale well, and it doesn't work well if you've got an undefined number of clients. So it's basically very easy to just point to whatever you saw earlier. But since we want to have our events as close as possible, we also want to add another property, a clock, a value where we increment every time we generate a new event. And to kind of prevent it from growing out of bounds, we can reset it every time that client discovers a new event from the server. And then we just need to order based on that causality. And the first key is the preceding sequence number, and then based on the client sequence that the client generates. I think visually, so this is how I'd illustrate causality tracking in events. So let's say that the last event with the sequence 18 was preceded by the event that's got the sequence of value of 17, and that one is preceded by another event, and we can have multiple events actually pointing to the same point in time or in history, and it can come from any client basically. And then we could finally reconstruct causal order from however the events were actually written onto the stream. And we just have to make some minor adjustments to our code. In our inbound and outbound reconciliation logic, every time we process those events, we just have to order them by their causality. And it actually then makes more sense for the logic to apply those events either to the model or when it needs to reduce the edit distance. And now we basically, now the order of our task make more sense in case a client was a bit slow when it came to publishing those events, or if it was offline. And we don't have to write these events in batches anymore. We can just shoot them onto the server in an unpredictable order, and we could reconstruct that order on clients since we've got all that information. And as I said, this gives us an ability to write events into our database in an unpredictable order, freeing us from those big sequential writes. So let's talk about advantages. As I mentioned in the motives, it's a very easy way to implement, synchronization for a shared data source because it minimizes the data redundancy. Its data structures are very lightweight and easy to transfer, so it's fast and it also doesn't burn that much bandwidth. There's very minimal server logic if you want to use stream-based sync. As I mentioned, we're actually writing very small data structures to our server, which means that we don't spend that much time writing these events into the database, which means that we allow more time for other clients to write their events, which means that we can have more users. And due to the simplicity of the data schema, it's very easy to distribute this kind of a database and scale the whole system up. And due to the causality tracking, we can afford offline support with no extra logic except for that ordering part. There's also drawbacks to this sync. So server simplicity actually means that there's more complexity on the client side. It has a little extra logic, and that's basically the outbound and the inbound reconciliation. And rogue clients, as I mentioned earlier, could generate a lot of unnecessary events, and then other clients would have to discover them and download them, and would slow down or worsen their user experience. One other thing is that we need to read the full stream in order to get into a fully consistent state on our clients, and that can grow out of bounds too. We could basically just say, all right, maybe we just need last 10 tasks because our app allows that, and we could just fetch those events from the stream. But the thing is, there's no easy way to discover where those events are on the stream unless you implement some indexing or something on top of that. Or you could implement some backtracking logic where a client would basically slowly read the stream in reverse. But it's due to the causality tracking, it just introduces a lot more complexity. And that concludes my talk. And I'd be happy to answer any questions, if there are any questions.